So let's go back to our slides. So here, what we see here is this probability distribution that we have plotted, and then we see that it has been fitted by a continuous kind of a curve, okay, a continuous PDF curve, okay, with respect to wind speed. And this kind of a fitted curve, if we see what type of function can fit this kind of a bar graph that is typically found in wind speed distribution throughout the world, the PDF distribution that works best is what is called the Weibull distribution, and we will see that what this distribution actually looks like. Okay. So wind speed at a location obviously varies with time, hence it is necessary to model the variation of wind speed at prospective location of a wind turbine farm, as we have discussed, and one can measure the wind speed at a given location and plot the hourly averaged wind speed distribution over all hours in the course of a year. Okay, so we discussed this. This is how the anemometer does this. Okay, that we find the number of hours for which a certain wind speed is measured and the number of hours that we and this we distribute in a bar graph in terms of the wind speed distribution. Then one can construct the probability distribution for hourly average wind speed over a year for a given location. And often the observed probability distribution can be fitted by what is called the Weibull probability distribution function. WEIBUL probability distribution function. It's a distribution function just as the Poisson distribution or the normal distribution. It's a different distribution function that is most appropriate, and this distribution function has this functional form. Okay, we use the function xi to express this Weibull probability distribution function. This v is the velocity, the wind speed values that is varying from say 0 to a certain maximum value. All right, and these two, capital S and V0, are certain parameters that we can adjust to adjust the shape of this distribution function. S is called the shape parameter and V0 is called the scale parameter. And the functional form is like this: S by V0 into V by V0 to the power S minus 1 exponential minus V by V0 to the power S. Remember, S and V0 are fitted constants. Okay, and V is the wind speed that is actually varying at that given location. Okay, S is the shape parameter and V0 is the scale parameter, which we are determining semi-empirically by fitting our anemometer readings with the Weibull distribution. So this figure to the right shows how the PDF function changes when we are shifting from one type of shape parameter to another type of shape parameter. Okay, so this is the unit of y is somewhat arbitrary, because obviously if it's probability it wouldn't go above 1. Okay, so this is actually non-normalized variable, but we will see that once we actually normalize it, it will all go below 1. Okay, so here the shape fact PDFs is S equals to 1, 2, 3 for respectively V0 equals to 1. Okay, so this is S equals to 1, the scale parameter S value is 1, V0 is 1. So it looks like a exponentially decaying curve almost. When the shape parameter is 2 and the scale parameter V0 is 1, it looks quite similar to a normal distribution, except that these are not going to plus infinity or minus infinity. These are kind of constrained within 0 and 2, for example here. Okay, but it is a kind of a peak and it goes down on either end. Then when S equals to 3 and V0 equals to 1, we see that the peak kind of shifts closer towards lower values of V and it becomes kind of broader. Okay, then for shape parameter 2, we have changed the V0 value from 1.2, 1.4 and 1.6. So S equals to 2, V0 equals to 1, we had this value. All right, then when S equals to 2, V0 equals to 1.2, we get this kind of value. So as the V0 value increases, you can see the shape is kind of becoming more and more broader. Okay, so higher values of V0 creates a broad shape. Okay, similarly higher values of S also creates a broad kind of a shape. All right. For smaller values of S, we have kind of a high peak that goes away quickly to zero at a smaller intervals, whereas the peak becomes broader and shallower as we increase S and V0. Okay, and when we have S equals to 1, then it becomes kind of an exponential curve. Okay. So that's the basic idea. So usually for a given location, S values range from 1.3 to 2.2 and V0 values range from 2.6 to 8. Okay, so clearly there is a large variation, but we can basically see that the shape parameter varies from 1.3 to 2.2 and the scale parameter V0 varies from 2.6 to 8. For our analysis, we will be modeling our wind velocity distributions using the shape parameter value S as 2. Okay, so we will use 2 as our shape parameter value, and in that case S becomes fixed, and if this becomes 2 by V0, V by V0 to the power 1 exponential minus V by V0 square. Okay, and you can see this expression here, 2 by V0, V by V0 to the power 1, so this becomes 2V by V0 square exponential minus V by V0 square. Okay, the specific probability distribution for which the shape parameter is 2 is called the Rayleigh distribution. Okay, and we will use the Rayleigh distribution to fit most of our models. Remember, V0 is still variable. You can still vary the V0 parameter to change the distribution of the wind speeds. Okay, for S equals to 2. So this is S equals to 2, V0 equals to 1, S equals to 2, V0 equals to 1.2, S equals to 2, V0 equals to 1.4, S equals to 2, V0 equals to 1.6. Okay, so you can change the V0 value still. Now, when we can model the PDF of a wind speed distribution function using Rayleigh distribution, we can find the mean value by directly integrating this term, and so we will integrate this from 0 to infinity PDF into V dV. Okay, this is the probability distribution, V into dV integral 0 to infinity, correct? And this becomes root over pi by 2 into V0. So the average velocity for a Rayleigh distribution based wind speed probability distribution is root pi by 2 into the whatever the scale parameter V0 value is. Okay, but we can also do it a little bit differently. Now that we know that for Rayleigh distribution the average wind speed is given by this function, we can replace V0 by 2 into V average by root pi. So 2 into V average by root pi we will put into each of these V0 square values, and then we get the Rayleigh distribution only in terms of V and V average. So it is very similar to the normal distribution. If you remember, in a normal distribution also the PDF was expressed in terms of the actual variable, say x, and the mean of the variable x bar. Okay, similarly in the Rayleigh distribution you are expressing the Rayleigh distribution in terms of the actual variable V and the mean velocity or mean speed V average, and this expression becomes pi V by 2 V average square exponential minus pi by 4 V by V average whole square. Okay, but remember, this V average either has to be evaluated semi-empirically or you have to choose a suitable scale parameter V0 to get the V average. Okay, so still V0 is there implicitly in the equation. So now that we know the wind speed distribution, the Rayleigh distribution with its average wind speed V average, we can now look at the wind power distribution. And here is a figure that is very instructive of what I have been talking about. Here an anemometer reading has actually been done in a location over an entire year, and the wind speed distribution has been expressed in terms of number of hours over an year for which that wind speed was measured. Okay, so for example, the wind speed of 5 meters per second was measured at that location for 500 hours over an year. Okay, whereas a wind speed of 10 meters per second was measured for around 250 hours over an year. So this is our wind speed distribution. Alright. The wind power distribution is, however, proportional to half rho VQ. Obviously the wind farm, we will assume the area of the wind turbine blades is the same. So that is pi d square by 4, the swept area. Okay, so that does not change from one location to the other or one time to another time of a year. So the area kind of comes out. So the wind power distribution is proportional to V cube is proportional to V cube. Okay, cube of that speed. Okay. Now clearly, if you can think, most of the power will be located at higher wind speeds. Okay, so the wind power distribution, if you can see here, is given in terms of megawatt hours. Okay, so remember what is megawatt hours? It's 1 megawatt into 1 hour. 1 hour has 60 minutes into 60. So 10 to the power 6 into 60 into 60 is what is joules. So 1 megawatt hour is that amount. Okay. So clearly, if you see, for a wind speed of 10 meters per second, you have 250 hours. Okay. Now 10 is 10 cube. Velocity is V cube. Okay, 10 cube. So 10 cube is 10 into 10, 100, 100 into 10, 1000. Okay. So 1000 and the hour is 250. So 1000 into 250. That will be the V cube that we are getting in terms of megawatt hours. Okay, we have to multiply it with half rho A to get the units in joules. Correct. For the value of 5, so that value in megawatt hours is given as 5 is given as this expression here. I am not sure what the units are. Okay, we will just check what the actual value of the unit is. Okay, whereas for a wind speed of 5 meters per second, okay, you have 5 cube. So 5 into 5, 25 into 5, 125. So at one end you have 1000 and this one was 125 only. Okay, so clearly, because it's a V cube dependency, you have far less value at a wind speed of 5 for power compared to a wind speed of 10 meters per second. So even though you have 500 hours, 125 into 500 is still much lower than 1000 into 250. Okay, and so the amount of power that is generated is much lower also. Okay, so even though you have lower number of hours, because you have a higher wind speed and you are cubing that, you have a higher power output in megawatt hours for that wind speed. Okay, so the wind power distribution always shifts to the right of the wind speed distribution, and higher amount of power is generated for higher wind speeds even though they happen at lower frequencies. Okay. So what we are saying here then is, suppose the wind turbine, the total available power in terms of megawatt hours is given by half rho A VQ, okay, over an entire year. And what is the contribution of each individual wind speed to the total power that is being generated over a year? Okay. This is given in megawatt hours. And we see that the contributions are much higher at the tail high end of the wind speeds compared to the more higher values that are present at lower wind speeds. Okay, so you get high power outputs at this end where you have very few hours for which these winds are flowing, but the speeds are so high you are getting much higher power output. So the wind power distribution is significantly different from the wind speed distribution, as the wind power is proportional to the cube of the wind speed. Hence, the wind power PDF is proportional to V cube into the Rayleigh distribution. Okay, the data and the distribution feed for wind speed and wind power are given. So this is the location in Colorado, USA. Okay, so this gives you the actual data for a certain location in US. Because of the cubic dependency, the wind power distribution peaks much later than the wind speed distribution curve, with 95% of the total power generation occurring for wind speeds greater than the most likely wind speed. So these values. Okay, so most of the wind power is generated beyond the most likely wind speed value of 5 meters per second here. Okay. So we can develop an approximate relationship between hourly average wind speed and hourly average wind power. The average wind power is 0.5 rho A V average whole cube, just as we showed in our example before. Okay, which is half rho A. Now integral of the Rayleigh distribution into V cube into dV. Okay, the average V cube is basically the Rayleigh distribution. So here we are using the explicit PDF that we are fitting into V cube into dV, and then if we integrate this, this becomes 3 by pi rho A V average whole cube. Okay, so the average power is given by this expression. So here V average is root pi by 2 V0. This becomes root pi by 2 V0 whole cube, and 3 by pi rho into A. A is the swept blade area, rho is the density of air. And this difference between the most probable wind speed and the wind speed corresponding to maximum power can be also shown by doing a differentiation of this Rayleigh distribution. So here we are fitting the Rayleigh distribution, and the most probable wind speed is the wind speed at which this Rayleigh distribution peaks. So you have a stationary point here. So if we differentiate the Rayleigh distribution with respect to wind speed and set it to 0, the velocity that we will get is the velocity of the most probable wind speed, and the V most probable, based on that we will get. So we are basically differentiating this expression here with respect to V, okay, and setting it to 0. And that V for that most probable point is root 2 by pi into V average. What is root 2 by pi? Pi is around 3.14. So this is less than 1. Okay. So the most probable velocity is lower than the average velocity. Okay. This is around 0.65 or 0.69 or something like that. You can just check that out. Okay. So if you see this speed distribution, the most probable velocity is here. The average velocity will be somewhere around here. Okay. Somewhat higher than the most probable velocity. Okay. Because it's a mean value, so the mean is always higher than the median. The most probable velocity is basically the median value for your distribution. In contrast, the wind power distribution is given by V cube into the Rayleigh distribution. Alright. So hence the wind speed corresponding to the peak power point, that is, we want to find the wind speed corresponding to this peak power point here. Okay. This is given by ddv of V cube into the Rayleigh distribution, and we set this into 0. Okay. So if we do that and find the velocity at peak power, VPP, velocity at peak power, this becomes 2 into the most probable velocity, 2 into root 2 pi pi V average. So the most probable velocity is half of the velocity at peak power. Okay, and this we can see here reasonably well. So this is 5, this is around 10 or 11. Okay, of course there is a slight bit of difference, but basically under ideal Rayleigh distribution conditions, if this is 5, this will be around 10, and this kind of shows the shift. And of course this is higher than the average velocity, because if you put 2 here, this becomes 4 into 2, 8 by pi, so 8 by 3.14. So this is more than the mean velocity as well. Okay. So this kind of shows explicitly that you are getting the peak powers at a velocities higher than the mean velocity, and certainly at velocities higher than the most probable velocity. Okay. And this kind of gives you the that same distribution a little bit more clearer way. Okay. So today I will stop here. In the next class we will continue this idea and see how we can rate wind turbine plants from this point on using the velocities, using velocity affability, right? Given a velocity distribution at a certain point, or given that you know the average velocity at a certain location, how much power can you expect out of the wind turbine, and how you can rate the wind turbine power output. So those things we will discuss in the next class. So thank you for listening. We will meet again in the next class. Thank you.